Uh, so we'll continue with our in the previous session I had discussed um, the interpretation and importance of various terms in Bernoulli's equation, and I was just talking about aircraft, how airfoil cross section, because of the pressure difference you get the lift, and what are the different forces acting on aircraft during its steady flight and all that. Okay, so with that background, we'll solve one numerical on say a typical Boeing aircraft numerical. Okay, why we are taking Boeing aircraft? Because as I told, there are two major aircraft makers in the world. One is Boeing, which is US based, and another is Airbus, which is Europe based. Okay, so most of the regional transport aircraft like A320 or Boeing 737 and all are some kind of 200 seaters, and when you travel a distance of say around 2000 kilometer, like from Delhi to Bhubaneswar, Bangalore to Bhubaneswar, so you use this kind of regional transport aircraft. So there are two types of aircraft. One is called regional transport, another is called continental aircraft. Suppose you are traveling from, let us say, Delhi to Heathrow Airport in London and all. So those are kind of 8,000 miles and all. So that kind of long distance, those are called long range and long distance aircrafts. Okay. So the question is like this. So this is the driving. So
Equation.
these are the three terms: pressure, velocity, energy, and the
Potential.
potential energy. So if we consider that
They are at same height.
there is they are almost at same height, you can neglect that, and this is the driving equation. So the question is like this: a fully loaded Boeing aircraft has a mass of 3.3 into 10 to the power 5 kg. Okay, so yeah, very good spec. Okay. Uh, okay, so a fully loaded aircraft whose mass is uh, 3.3 into 10 to the 5 kg, right? So this is my aircraft. Okay, so let us say uh, okay. So okay, so this is the airfoil cross section. So you have a, well, let us say weight. You have a weight acting like this. Okay, this is your weight, and then you have a lift, lift, right? So there are two things. One is, any structure, the weight acts at the CG. Okay, whereas this lift will act at some other point. It will act at some other point, which is known as the center of pressure. Okay, so if you see, the lift is equal to the weight, right? The lift is equal to the weight, right? But they are not in passing, those two forces are not passing through the same line. Okay, so because of that offset, there will be some moment created. Okay, so that particular moment, to balance that moment, in the tail plane you will have another small wing, right? Kind of, that is called the tail plane. So you, in the rear, you will have some kind of, yeah, some kind of tail plane, right? So that will create a force which will balance that imbalance moment. That is the need. That is why you need a tail. Okay, because there is a imbalance moment that is being balanced by some forces created at the tail. Okay.
Right.
So the cross section of the tail is also something similar to that of the wing, right?
Yeah.
So if you cut the wing, yeah. So I think we can just, for a better representation, let us put it like this. So this is your tail, and maybe some upward or downward, some kind of force will be acting there. Okay, to balance it out. So the question is like this: the mass of the aircraft is mass m is equal to mass of aircraft is equal to 3.3 into 10 to the power 5 kg. Okay, 3.3 into 10 to the power 5 kg. So uh, which is otherwise like 3.330 into 10 to the 3 kg, right?
Yeah.
Which is equal to 330 ton, right? So 1 ton is equal to 10 to the 3 kg. That you should remember. So that is given, and so the let us say the aircraft is in level flight. Okay, in steady state it is in level flight with a speed of, and it is traveling at a speed of 960 kilometer per hour. Okay, let us say my aircraft is moving at a speed which is v, so that particular v is kind of 960 kilometer per hour. Okay, so it's a subsonic aircraft, so less than 1120 or what. So my aircraft is traveling at a speed of 960 kilometer per hour. Okay. So the question is, estimate the pressure difference between the lower and upper surface. Okay. The first part of the question is estimate the pressure difference between lower and upper surface. Uh, That's the question. So how to do it? Okay. Uh, okay. So your estimate the pressure difference between lower and upper surface of the wing. Okay. And in this case, another input is given, the surface area of the wing is the speed of the upper. The wing area is 500 meters square. Okay. So another input that is given is, okay, another input that is given is wing area. Okay, wing area is equal to 500 meters square. Okay, so that is another input. Okay, your speed is given, your wing area is given. Okay, and another input that is given is the density of air. Okay, so this is wing area. So one is, this is one thing, this is two, this is three, is density of air. Density of air is equal to 1.2 kg per meter cube. So you just remember that water is 1000 kg per meter cube. So as compared to water, air is almost 1000 times lighter, and the density is 1.2 kg per meter cube. So with these input, he is asking what will be the pressure difference, estimate the pressure difference between the lower and upper surface of the wing. Okay. So you just remember, you have a aircraft, you have everything, but that wing is the only thing which is creating the lift. So if you take a picture of this, the aircraft top view, okay. So the when you see from the top, it will look something like this. Okay. So this is your aircraft. Okay. And let us say it looks like this, and your wing will be looking like this. Okay. This is wing. Okay. So they have given, so the pressure difference is happening between the upper and lower surface of the wing. So these are the two surface area of the wing. Okay. Let us say this is left side, this is right side. This is right side. Okay. So this is called left wing. This is called right wing. Okay. So the surface area that he has given is because the pressure difference happened only on the wing surface, not on these things.
Yeah.
Okay. So this is my surface area. So this is my complete surface area. Okay. So the area, so area of wing is equal to, it is given as 500 meters square. Okay. 500 meters square. Okay. So you can think in terms of number. Okay. Let us say 500 means left is 250, right is 250. So 250 you can think as if my length of this wing, if you consider it as rectangular, this is 25 is the length, and let us say this width is, let us say 10. Okay. So you can imagine like how much is 25 meter. Okay. Let us say this room is, maybe it is 5 meter. So 3 times the length of this room is something like 5 times. Okay. 5 into 5. So that is one length,
Just one
length
wing.
of one wing. Okay. So that long it is. Okay. 25 meter and 10 meter is the width. So area is around 500 meter square. Okay. So with this area, now you know the area. Now you want to find out the pressure difference. Okay. So actually, if you see P1 minus P2 is the difference between pressure on the lower surface and the upper surface. The lower surface has higher pressure, so I can say this point as 1. It is the higher pressure, and 2 is my lower pressure, right? So P1 minus P2, that is the pressure difference. Okay. So P1 minus P2 into area, okay, is equal to the weight. Because P1 minus P2 into area is nothing but your lift. So you know my lift is equal to weight. So where from lift comes? Because of pressure difference. So lift is equal to pressure difference into area of the wing only. Okay, not the area of the aircraft, only wing. So P1 minus P2 into A is equal to my weight. Okay, so they are asking the pressure difference. So my pressure difference P1 minus P2 is equal to, let's say, my weight W divided by area. So that's the answer. Okay. So finally my P1 minus P2 and now my weight. Okay. So weight, it is given as kg. I have to convert it into Newton because weight is a force and I have to convert kg into mass into force. So that is nothing but your 330
into G
into 10 to the power 3 kg, okay, into 9.8. Let us say that is another 10. Okay, let us consider it as 10. Okay, then divided by 500. Okay, so this is meter per second square. So this becomes Newton, denominator becomes meter square. Okay, so finally it will become 330 into 10 to the power 4 divided by 500, right? So the P1 minus P2 finally will be equal to 330 into 10 to the power 2, right? 2 divided by 5, right? 5. So this will become 66 into 10 to the power 2 Newton per meter square or Pascal. So that is the answer. Okay. So 6600. Okay. Yeah, this is some 6600 Newton per meter square. If this is the answer. Okay. This is the answer. Okay. That's the pressure difference. Okay. So till now, so that's one part of the question. Then we will move to the second part. You take a picture, then we will move to the second part of the question. Okay. So the second part of the question is estimate the fractional increase in speed of the speed of air on upper surface of the wing relative to the lower surface. Okay. So the question is estimate estimate the fractional increase in speed of air, the fractional increase in speed of air, speed of air, speed of air on upper surface of the wing relative to lower surface. On upper surface of wing relative to lower surface. Okay. So let us draw the wing. Just let us draw the wing. Okay. And this is my wing. Okay. So let us say this is my upper surface. This is my lower surface. Okay. And so this my aircraft is moving. Okay. When the aircraft is moving like this, the the aircraft is moving. So my air will approach like this. It will cut the air like this, right? Okay. So let us say this V2 is the speed of air on the upper surface, and V1 is speed of the air on the lower surface. Okay. So V2 is speed of air on upper surface. Surface. V1 is speed of air on lower surface. Okay. So you know that V2 will be like because the pressure is less there, velocity will be more there. So V2 will be more than V1. That we know. Okay. No. Okay. So you want to find out the fractional estimate the fractional increase in speed of air on the upper surface of the wing relative to the lower surface. Okay. So this is something like this. Fractional increase means that is V2 minus V1. Okay. V2 minus V1, that is the fractional increase of the speed of air on the upper surface. So V2 minus V1 is the increase in speed of air on the upper surface with respect to lower surface. Okay. V2 minus V1. Okay. Surface upper surface wing relative to the lower surface. The speed of air on upper surface wing relative to lower surface. Okay. So this is the difference. Okay. So this you want to find the fractional increase. Okay. So ideally it should be V2 minus V1 by the average velocity. See, this is upper lower. I want to find the fractional increase with respect to the average velocity. Yeah. Okay. So this is V2 minus V1 divided by V average. Okay. Because I just want to see with respect, let us say here it is V average. With respect to the free stream velocity, what is the increase in velocity on the upper surface? So it is V2 minus V1 by V average, which is nothing but V2 minus V1 by half V1 plus V2, right? Yeah. That is what we want to find here. Okay. So we have written the equation like P1 plus half rho V1 square is equal to P2 plus half rho V2 square, right? So that means half rho V2 square minus V1 square is equal to P1 minus P2, right? Yeah. Yeah, so this P1 minus P2 is otherwise we can write it as delta P. Okay. So half rho V2 square minus V1 square is equal to delta P, right? So that means half rho V2 minus V1 is equal to delta P divided by V2 plus V1, right? Because V2 square minus V1 square is equal to nothing but this, okay? So that means V2 minus V1 is equal to, okay, V2 minus V1 is equal to 2 into delta P divided by
rho into
rho into V2 plus
V1.
V1. Okay. So you have come this far. Okay. So now this V2 minus V1 divided by this half, if it goes down, it will become V2 plus V1 by 2. Okay.
Yeah.
Which is nothing but your like say V2 plus V1 by 2, right?
Yeah.
This term.
Yeah.
So that is yeah.
If
Okay,
that
so
happens, then V2
no, no.
minus V1 will go to number.
So V2 minus V1 is equal to 2 delta P divided by rho into V2 plus V1, right?
Yeah.
So yeah. So
If we take reciprocal, then this will also be reciprocal.
So V2, so this becomes V2 minus V1 is equal to 2 delta P divided by rho into V average, right?
Yeah.
Yeah, V average, that is, right? V average.
Mm-hmm.
So then you want to find V2 minus V1 divided by V average, because you want to find the percentage, okay? V average, okay? That is equal to delta P by rho into V average square, right? V average square. So that is the fractional. So this is a fraction now.
Mm-hmm.
Okay. So you already have got your delta P to be 6.5 into 10 to the power 3 Newton meter square. So your delta P is already, we have found in the first part. We have already calculated as 6500 Pascal. Okay.
If you take 9.8, then
6500 Newton per meter square. So that is your delta P already. Okay. And at the beginning, the input was the velocity of the aircraft. Okay. So that was nothing but your V average. Okay. Which is nothing but your 960 kmph. 960 kmph. Okay. So now you want this term, right? You want this, right? If you multiply by 100, you will get the percentage increase.
Yeah.
So what is the percentage increase? That is with respect to average.
Understood.
Aircraft is moving at 960 kmph. So when it is moving through air, on the top surface there will be increase in velocity, on the bottom surface there will be decrease in velocity. So that V2 minus V1 is the increase in velocity with respect to average. That fraction you can find out. You know now delta P is equal to 6500 Pascal, and density of air was given as 1.2 kg per meter cube, right? So density was 1.2 kg per meter cube, right? So that also you know. And V average is 960, that also you know. So on the right side you know everything now. Okay.
Yeah.
So if you replace all these value now, you will find the answer to be 0.08. That means it is 8%. Okay. So this is by solving with the actual real world problem, you can have a feel of the number. Okay. So rather than doing some theoretical one, if you do a real world problem, you will find a feel of the number. See, now you got to know that aircraft travel, a subsonic aircraft, it is traveling at 960 km per hour. and the velocity on the upper surface increases by 8%.
Yeah.
Okay, that also we have found. And the pressure difference between the lower and upper surface also you can find out to be some 6500 Pascal. So you get a feel of all these numbers. So now we can understand how the Bernoulli principle is being applied in aerospace engineering for designing a aircraft structure like a wing and all. Because when we start a conceptual design of aircraft, first the designer will be given, okay, this is going to be the weight of the aircraft. So based on the weight of the aircraft, you will decide what is the pressure difference, right? So if you know this is my pressure difference, based on the aircraft weight, you will know what should be the lift. If I know the lift, then if I know what will be the velocity difference and all, I have to design, okay, this is going to be my wing area. So once I find, okay, my wing area is this much. Once I find out, like say here, they have said my wing area is 500 meters square. Then I design the wing. Okay, left wing will be 250, right wing will be 250, like that. So when a designer designs an aircraft, he will know the weight of the aircraft. Corresponding to weight, what should be the lift? Once he knows the lift, then he will have an idea of, okay, 8% increase in the velocity this airfoil can provide.
Yeah.
So if there is 8% increase in velocity, what should be my wing area and all that? That a designer need to calculate. Okay. So that's how in aerospace engineering they do the conceptual design, then preliminary design and detail design. Okay, but you can see the physics behind it is the driving force. Okay, engineers put numbers, but there is a physics behind it. It's all from the Bernoulli's principle. Okay. Okay. So in the next session we'll touch upon some other real world applications of Bernoulli's principle, like say Magnus effect, and how the deposition of fat causes constriction and that causes heart attack. How it is being driven by Bernoulli's principle, that we'll discuss in the next session. Okay.